My name is Dr. Jonathan Buonocore, and I'm presenting to you today some of our research called Quantifying Patterns in Seasonal Energy Use in the United States and the Implications for Decarbonized and Healthy Energy Infrastructure. This is some research that I've worked on along with Dr. Parashar and Dr. Joe Allen, all at the Harvard Chan School of Public Health in the Environmental Health Department. So where this kind of started out with was thinking about the future energy planning models, evaluating those to try and figure out what futures with building electrification could look like. And when you're going through this, we realized that these models are largely focused, and rightly focused, I would say, on the electrical grid and largely on annual generation projections. And largely they're focused on modeling different scenarios for scale up of renewables and for phase out of fossil fuels. And when there's some element of sub-annual time examined, it is usually looking at meeting hourly demand and reliability requirements, largely focused on the now famous duck curve from California, where there's this big issue with late afternoon and evening ramp up of electricity that needs to be met just at the time when solar electricity, the sun's going down, so there's a lot less generation from solar, which is a big issue, especially in Southern California. And with the idea of electrifying everything becoming an emerging climate mitigation strategy, which is a good idea, again, because we can remove combustion, which is good for both climate and health. One of the big questions that we're seeking to answer here is, what will this mean for the electrical grid? So the big questions for us were to look at, based on historical data, what does the seasonal variation in total energy demand, really importantly here, not just electricity, look like? How is this seasonal demand currently being managed? What are the implications for electrifying buildings? And really specifically, if we do follow the strategy of electrifying everything, what demand will this put on the electrical grid? So to figure this out, we looked at the monthly energy production data that's available from the US Energy Administration for as much as was available. So we were able to get historical data all the way back to January 1973 up through September 2020. So we were encompassing a period of almost 50 years. Took the monthly average and evaluated some prototypical scenarios of fossil fuel removal using this pre-existing electricity loss rate that we got from the data. So I'm going to go through some of this analysis showing what the data is and some of the scenarios and talk through some of the implications here. So this is data showing where energy that was consumed by electrical buildings came from 1973 to present. Two big players here, as you can see, electrical consumption and electrical losses, all generally increasing over the time period, hitting a peak around the year, say that's about 2008, and then decreasing a little bit afterwards. You can see also there's this big seasonal swing in terms of natural gas use. And similarly, you can see this seasonal swing in the use of petroleum for heating, although that total use in general of petroleum has been decreasing over this time period. The trends are a little bit different for residential buildings. You can again see there's this general increase in the consumption of retail electricity and an increase in electrical losses. And you can see also there's this really big swing in the use of natural gas for home heating, with these really big spikes in the winter months and these valleys in the summer months. You can also see kind of a similar parallel trend again with petroleum use, where again you can see the wintertime peak, but similar to commercial buildings, there's been less and less petroleum getting used in buildings for building heating as time went on. So looking at the monthly averages now, you can see on the left here, there's just all the energy consumption converted into three different categories here. There's the retail electricity consumption, there's the electrical losses, and then the total primary energy, which is again that wintertime heating, where you can see there's this really big increase, really big peak in the winter months and this really kind of deep valley in the summer months. Whereas with electrical losses, you can see there's this typical kind of summer peak that we think of. On the right side, it has this energy consumption disaggregated into different field types. Again, the electrical losses and retail electricity dominate, giving us the kind of traditional peak that we think about with electrical generation. But you can also see in this right panel, there's kind of a reverse trend with the heating fuels where largely driven by natural gas and petroleums, you see this really large peak in wintertime consumption and a bit of a valley in summer. It's a similar and even more straightforward picture for residential buildings. Where again, you can see the typical summer peak with electrical losses and electrical consumption, and then the wintertime peak of the consumption of all the other fossil fuels or all the other fuels. Broken down similarly, again, you see your typical electrical losses and electrical consumption with the big summertime peak, and then very large, almost over 2,000 trillion BTUs of total energy being consumed in the winter, largely driven by natural gas and by petroleum use, largely for heating in, again, the winter months with the peak in January. So we have this gap existing already, covering energy, presumably storage, or this kind of seasonal fluctuation. So a good question to be asking is, how are we currently managing this gap? So you can see here at the top of this, there's total consumption in gold, and then there's total production in blue. So, and they don't follow each other. So there's clearly something else going on here. Breaking it down by the different industry uses below, you see the patterns that I showed earlier for residential and commercial building consumption. You can see a bit of a bump in consumption with the electrical sector as well. And it's not enough really to totally cover the variation that you can see here. So really what's driving it is this big role of gas storage, where you have natural gas being produced and then being injected back underground, where it's stored and usually withdrawn. The withdrawal season usually starts in about October and ends in about March, where gas is being pulled out of these storage facilities to be used for building and heating. And you can see here some of the regression statistics below, where the R squared, which is the ability for these two variables to explain each other, increases by a lot when you add storage, indicating that storage has a really big role to play in managing the seasonal gap in supply and demand of natural gas here. Breaking this down again by monthly values, you can see the same patterns as we saw before. There's production and total consumption that again aren't mirroring each other, where consumption goes below production in the summer months, and there's a lot more being consumed than is being produced in the winter months. Again, that gap is being made up by gas being pulled out of storage during the winter months while it's being injected in the summer months when there's less gas being consumed. So what really this means for us is that we have a fleet of batteries that are taking care of basically acting as battery for building heating that many of us overlook and didn't even know we have. There's 412 of these facilities in the country operating largely in areas where there's historical oil and gas production or aquifers and occasionally salt domes. And again, these areas, there's gas injected into them during the summer months, and the gas is withdrawn from them in the winter months, providing natural gas for heating for buildings in the US. These underground gas storage facilities are not issue-free, unfortunately. They are often near people. Many of them are repurposed oil fields and wells. An analysis that I was part of a few years ago showed that the median age of these wells is about 78 years now. And they do leak occasionally. The most dramatic version of this is the leak in Aliso Canyon in California, just outside of Los Angeles. This event, it was the largest accidental methane release in US history. And along with the climate impacts, there's also a fairly large health impact for the area, where close to 6,000 homes had to be evacuated. And there were reports of people experiencing all sorts of odd health symptoms, including nausea, vomiting, vertigo, bloody noses, and other other health impacts that were associated with this event. And to this day, there's still issues with energy reliability in Southern California since the storage field is still offline. So the question is, we have this gap, we have the infrastructure we have that's currently managing it. So the question is, what would this gap look like under different degrees of building electrification? So as is right now is on the left, and you can see what this looks like on the right if we were to kind of basically swap out and electrify 50% of the existing fossil fuel use and converted it to electricity, assuming the current rate of loss. Right now, the gap is a roughly 1,400 trillion BTU per month gap, where it's at about 37.36 in January and 23.36 in October. This gap almost over doubles to being about 2,800 trillion BTUs wide, spanning from January to September, going from about 5,600 to a little over 2,800 in September. And this again assumes that we have the same losses as current. If we were to go all the way to 100% electrification, we again have the same gap on the left, and on the right here, we'd have this gap that's now double what it used to be. And it's over 4,000 trillion BTUs per month, gap again ranging from January to September, where we have a consumption of about 3,269 in the month of September, and we have to get up to a rate of 7,488 trillion BTUs consumed in September. So it's a very, very large gap that we have to fill. So conclusions and next steps here. It does appear that there's this very large seasonality in heating demand, and this may present a major challenge for building electrification in the future. And because of this, the performance of electrified building heating is going to be a key component of this. We looked at loss rates before, but there's varying efficiencies of these different technologies, whether it's heat pumps, geothermal, or other technologies. And the performance of these technologies is going to be key in determining how good they are with handling this seasonal gap. We do think that any strategy for electrifying buildings, it really should be tested for performance against the seasonal variation, since it's going to be a big obstacle to be overcome. And kind of if you take this framework a little bit further, if you think about it, sort of oil tanks, gas wells, wood piles, and anything else where we're storing heat energy, it's basically just a battery, if you think about it. So with that, we think this curve needs a name. We decided to call it the Falcon curve as an homage to the duck curve. There's two good reasons for that. The first is because it kind of looks like a bird with its kind of wings splayed out like that. But more importantly is that the Millennium Falcon can dock right in the top. So with that, thank you, and looking forward to talking about this more.